To determine our optimal parameters, we will be minimizing our target function or our objective function. The objective function we will be using is the residual sum of squares. So we look at the sum of all the squared residuals. If we look at it, we had the model. So in our model, we had y hat was theta 1 times phi 1 plus theta 2 times phi 2 plus and so on up to theta n par phi n par. So in this, the theta values, these are the parameters that you want to estimate. The phi's, they are the different variables. We have this for n observations. So we get basically a set of these equations. So we get it for each of the observations separately. So for the first observation, you have this. So it's theta 1 times phi 1, 1, plus theta 2 times phi, first observation, second variable, plus and so on, up to the last one, theta n par phi, for the first observation, the second or the last parameter. You have the same for theta y hat 2, which is then theta 1 plus phi 2, 1, plus theta 2 times phi 2, 2, up to theta n par phi 2 n par, and you have this until you get to yn. So you can write this also as a matrix. So if you have this, it becomes y1 hat, y2 hat, up to yn hat, equals, and then you get the matrix of all the phi's, so the variables, phi 1, 1, phi 1, 2, phi 1 n par, up to phi n par, times theta 1, theta 2, theta n par. So you can write it as a matrix notation, and you can plug in this matrix notation inside our minimization function. So what we have here, so basically this is the reduced version of the matrix notation. Y hat, which is this variable or this column vector, is phi times a vector theta. So this is written in matrix notation, linear model in matrix notation. Y hat is the vector of the model predictions, phi is the matrix of the independent variables, and theta is the vector of the parameters. So phi is completely measured. So it's filled with values that we know, that we observed. So what we then do is we substitute this in our objective function, and basically the objective function in matrix notation becomes y minus phi theta transposed times y minus phi theta. To solve this, we had to derive. So we derive the objective function to theta. In this case, it's matrix derivation. So we have a function we derive to each of the theta. It's minus 2 times phi transposed y minus phi theta. And then you can solve this, so you can easily take out theta by just noticing that this is minus 2 phi transposed times y minus 2 phi transposed phi theta equal to 0. You want to have theta on one hand, so it is, this becomes plus. This is the plus. So it is then 2 phi transposed phi theta equals to 2 phi transposed y. Or, this cancels out, theta is the matrix phi transposed phi inverted to bring it to the other side, because we are working with matrices, not with numbers, times phi transposed times y. And so we see here that we have an explicit formula for the solution, which is given by this formula. So in matrix notation, it looks like this, and so this is only for linear parameters. So this doesn't work for nonlinear parameters, but we do know the measurements, we know the y measurements, we know the measurements for phi, and so in the end we get an estimation for theta based on our observations, explicitly in a formula. The only thing is, you have in this phi transposed phi minus 1, so we can only calculate it if this matrix is invertible, so if it is of full rank. If we have a nonlinear system, it's impossible to get out the theta. So in this case, let's say we have a system y is x to the power theta. We plug it into our objective function, so you have yi minus xi to the power theta squared, and you sum. And then you minimize, so you derive with respect to theta. If you derive with respect to theta, you get xi to the theta here and then xi to the theta there. You work them out, you get to the last line, and you see it's impossible to get theta out. So you cannot find an explicit solution theta equal to something. So here, what we have to do is we have to rely on another way, on a numerical iterative process to find this optimal solution. So this iterative process is very simple in itself, but the details, they might pose some problems. First of all, you have to start with an initial parameter estimation. So you have to start somewhere. You have to start in theta 0. Theta 0 being the initial estimation. So you have to take some values for theta, which you think will give us a good solution for the iterative process. So you base yourself on this theta 0. You simulate the model. You calculate the objective function based on this initial parameter estimation. You compare the objective function to what it could be or how to minimize it. You look how you can make it smaller. Based on that, you propose a new parameter set theta. So you get a new number of values theta 1 up to theta and par. You plug it into the system again, you simulate the model, calculate the objective function, and so you continue until you get to a certain stopping criterion. So at a certain time, you will get convergence, or you get close enough to the objective, to the optimal values, and you stop at that time. What you have in this case, you have a problem with local minima. Because you have an iterative process, it can happen that you get stuck in a local minimum. Once you are in a local minimum, there is no guarantee that you can leave it, or sometimes you can leave it only with large difficulty. So you will need a lot of steps to get out of the local minimum. Sometimes you are stuck there, you can never get out. In the left side, this one is a linear problem. So this is linear in the parameters. And we see that here it's very nice. You have ellipses for the different values of the objective function. And you have clearly here, this is my optimal solution, and there are no local minima. So if you have a linear system like this, it means that there is only one global minimum and you are not confronted with local minima. So to recall how to look at such a plot, you have the plot theta 1 and theta 2. These are my two parameters, so I have a system with two parameters, theta 1 and theta 2. And then actually on top of this, you would have another axis which corresponds to the values of the objective function. So you have here theta 1 and theta 2, which are in the plane. And then on top of that one, you have an axis which corresponds to j theta, so the objective, the values of the objective function. And each of the lines, each of the ellipses, is basically a level of j theta where we made a cross section, so where we cut through that level, and then we see how the theta 1 and theta 2 correspond to this level of the objective function. So if you want to translate this back in 3D, you would get basically something like this, which looks like a cone going to the minimal value. So you have basically all those ellipses which correspond to different heights of my objective function. On the right hand side, this is a nonlinear system. And you see that you have a global minimum and a local minimum. And depending on how you approach the global minimum, where you start, you can get stuck in the local minimum. And Once you're in there, as said, this can be difficult to get out. So this line, the black line, this is a cross section which is corresponding to this. So what you see is if you follow this cross section, so if you arrive from, let's say, this side, so this point, and you follow in the direction of the black line, what you do is you arrive here and you go to the local minimum. Going to the local minimum means that here you will find the minimum. And depending on how your iterative process is working, depending on the step size you will be taking, it can be that you get stuck. So that's a difficulty with a nonlinear problem. With a nonlinear optimization problem, there are local minima and you can get stuck in those. The minimization algorithm is in itself not too difficult. The steps are always the same. So you look for the optimum, you start from the initial estimation. So the initial estimation, as we said before, is important because it will help speed up or slow down your process. If you take a good first step or a good initial estimation, you can arrive very quickly to your optimal solution. If you take a bad one, it can be that you never arrive there. So if here we would take this as my theta 0, so my initial estimates, I will get here in relatively few steps. So I move from this point to the optimal directly. If I start from this point, so the lower one, and I move here, I have a lot of chance to getting stuck, to be attracted to the local minimum, and I don't know if I can continue. So depending on where you start, the optimization to the global minimum can be more smoothly or more difficult. But what you do is you have that estimation, so you have your values for the parameter, initial values for the parameter. You look for a certain direction in the parameter space. So in which direction am I looking? What is the best direction to minimize? And the choice of this direction depends on the process, the algorithm that you are using. Then you minimize the objective function in this direction, and this gives you a new parameter set. So basically what you get is my parameter set in step k plus 1. So theta superscript k plus 1 means it corresponds to step k plus 1 in my iterative process. It's my previous values, so it's theta k plus a step towards the minimum. So I have an alpha k, which is a step size, times sk, which gives me the direction in which I am minimizing. So you choose a direction and you take a step towards the minimum in that direction. Alpha k, step size, in machine learning we call it the learning rate. So how fast or how far will I go in the direction in which I am minimizing. Alpha k can be different for every step or can be the same for every step. Also depends on the algorithm you are using. And then you repeat this principle until you find your optimum. So until you find your minimal value of the objective function, and then you take the theta values which correspond to that. So what you need is an initial estimation, so a good starting set of parameters, and you need to have a stopping criterion. When is it stopping? When did I reach, or when am I close enough to my optimal values of theta? There are different algorithms, and in C you can distinguish between two large groups of algorithms. A group which is gradient based, so which uses the derivative to find the direction of optimization, and then a group which does not use this derivative. Within the gradient based methods we will see steepest descent, Newton, Gauss-Newton, and Levenberg-Marquardt. For non-gradient based methods we will look at direction set methods, Powell and Brent, simplex method, and a global minimization.